Hello, so there is a lot of confusion among the students regarding the series and the parallel connections. So when we talk about a series or a parallel connection, so in series you basically, if I'm drawing a resistor, you are seeing these two resistors are there. So if they have one common point, suppose you have a thread, okay, you have this is one rod, okay, rod number one, and this is rod number two. And if you join the rod number one and the rod number two at one point, like there's one connection between one thread, so we have joined this rod 1 and rod 2 at a one common single point, so this type of connection is called as a series connection. And now when we talk about the parallel connection, so in case of the parallel connection, I will draw it like this. Okay, so this is the parallel connection. So in the parallel connection, you look at rod number 1 and rod number 2 are joined commonly at the top end and the bottom end. So there are two connections and the top and the bottom connections. So this is very important. Now, when we are talking about any circuit, suppose I've drawn a circuit. So there's a supply, DC supply, usually in experiment you are doing in the laboratory. So this is 0 to 30 volts supply and 0 to 2 ampere of current. So this is one resistor, this is another resistor, and this is another resistor over here. Now, in such type of connections, whenever you are making any connection of such type, okay, so I'll explain you one fundamental thing. Whenever you have to solve a circuit, what you have to make into take into account is that you need to label the circuit. Okay, so I'll label the circuit, start from the start point, okay, A, until and unless there is no any element connected in between. What is an element? An element can be a resistor, okay, it can be a voltmeter, ammeter. Ammeter is basically connected in series or any other stuff. So the potential of the point will not change. So this potential A will remain up to it, but across this there is a different potential. This potential over here would be B, okay, and same up till here. Now you see that this potential, now one more wire has come. So whenever you have to solve a circuit, first solve from in a series way, okay, like this. Then you take the parallel connections into account, A, B, and now this potential is C. Now across this, if you see there is one more resistor, so the potential of the point will change, D. Now you can write this point as E, but what I do is that since there is no element connected in between, so this potential remains same. This potential remains same. Why is it so? I will tell you. The resistance of a wire, okay, usually the resistance of a wire is very low. If you measure with the multimeter also, it will come around 0.001. Okay, so 0.001. So if you have the potential drop basically according to the Ohm's law is I into R. Okay, so the potential drop I into R, suppose you have a 2 ampere of current and your resistance of this wire is very low, that is approximately 10 power minus 3. So this is nothing but 0.0002. So what happens is that if there is no element connected in between, the potential of the point almost remains same. Hence, we have kept this point as D, this also D, this also D. We could have written this as E, but E, this as F also. But the potential remains same. Now to identify whether which element is in series, which element is in parallel, we can look at this particular circuit. So if you are looking at this particular circuit, so you can see that here in this circuit, there's a common point. There's one common point, that is C over here. So that means this, if I write this as R1, this is R2, this is R3 and R4. So I can safely say that R3 and R4 are in series because they are sharing one common point. Okay, so this circuit can be reduced. Now it can be drawn V, and this is your R1, this is your R2, and this is your, this I can write like this, okay, and this, wherein this is your R3 plus R4, and this is your R2 and R1. The same circuit, this very same circuit can be redrawn also. I'll redraw it over here. Okay, the same circuit can be written like V. Okay, R1, R2, R1, R2, and in this fan, instead of here, I can write this as R3 plus R4. So you notice that here too it is very visually looking that R2, R3 and R4 are parallel. But what about this? Again, if you start labeling it, this point is A, okay, potential will be this point across it is B, across it is C, across it is D, and this point is D, there is no element, this point is D. So you see that BD, okay, this point is connected between BD and this point is connected between CD. So in this case, if you look at this particular circuit, so it is not looking like that it is connected in series or it is connected in parallel. So if it has to be connected in parallel, so the potential of these points should be same. So this R2 is connected between B and D, and this R3 plus R4, if you look at R3 plus R4, uh, technically speaking, so this point is B. Across this, the potential should be, if this point is C. So you look at this point is D, okay, this point is D, but there is no element connected between D and B. So across this also, this potential of this point C would be same as D, right? It would be same as D. So we can safely say that C is equal to D. How we can safely say that? Because there is no element between this and this point. Hence, we can say that here also R2 is in parallel with R3 plus R4. Now, coming back to the circuit, I'll rub this here so that he'll be understanding. Now, this parallel and series, I hope you have understood. Now, the thing is that now let me reduce the circuit and apply the same formula to the bigger circuits so that you don't get any confusion. Let's see. Let's go about it. So now let me take the pen. Okay, let it be. Okay, so now this can be reduced as R1. Okay, R2, and this is R1 and R2 parallel with R3 plus R4. And now there is a voltage source here V, and this is your, now again you label it, this point is A, this point is B, and of course this is C and C. So there is only one common connection between this. So hence the R equivalent would be equal to R1 in series with R2 parallel R3 plus R4. Hence we can say R1 plus R2 parallel R3 plus R4 would be the R equivalent resistance. Now let's consider a bigger circuit. Okay, let's see for a bigger circuit how it works out. Same thing will be applying, so don't worry about this. So I make a circuit wherein this is V, this I write as R1. Okay, then this is my R2. Okay, now what I do is that I connect one more resistance here and I write this as R3, this as R4. Okay, and from here I connect one more resistance, this as R5, and let me connect one more resistance R6, and let there be R7. Okay, so if you look at this circuit over here, you label this circuit first. So this point would be A, and this point across this would be B. First, you go from, see, whenever you have to solve such kind of problems, what you have to make sure is that you have to grow from one side to another. Start from here, okay, here, and start labeling like this in an order. Then you have to take care of other points. Okay, now in a similar manner, what I'm doing is I'm trying to take these points and I'm going to label it in one particular direction. Okay, let me take the same ink color. This point is A, this point is B. So this point is your C, right? And across this point, this is D. Then you see over here, this is E. We can write it as F, but there is no any element connected in between. If there is no any element connected in between, whether it be resistor, diode, capacitor, inductor, the potential will remain same. As I have shown you, the potential drop is very less. So let this point will be E and this point would be also E. Now, when if you look at between R6 and R7, there's one common element. This is the common element. So this circuit gets reduced. This R6 and R7 are in series. Now, if you look at this point, okay, over here between, I'm talking about, now let's reduce this circuit again. Now, if you look clearly, there's a voltmeter over here, okay. This point is connected between A and E. This point is connected between B and E. This is B and C. This is C and D. Now, first, when we are going to reduce this circuit, we'll notice this, okay. This circuit, okay. So this is a random circuit which I have taken. So here I know that this point is getting reduced to R6 plus R7, and my final circuit is somewhat like this V, and this is my E point. Here there's nothing. So again I'll write this as, again I take label it A B. Okay, B point would be up to here. Okay, up to here B point. Then C. C means this is C. After that you have this D point. Okay, then you have E point, E point, E point. Clearly you can see now the circuit was, this was R1, R3, R2, R4 and R5. Now you can clearly see R5 and R6 plus R7 are connected between D and D, right? So what are the points between D and D? These are the 2 points. R6 plus R7 is in parallel with R5. So this circuit can be again reduced. Okay. Can you see any other element? See, this is C and D point, this is B and D point. Now you cannot do anything. So let's redraw it. Okay. Okay. So let's redraw it. So this is R4. And now what we have is that we have these points are in parallel. Okay. So let me draw this R3 point as it is. This is your R1. This is your R3. Okay. This is your voltage source as it is. This was A and E. Okay. This is your, okay. Now you reduced it like this. R1, R3. Okay. This point was your R4. And obviously you know the entire thing. This thing is in parallel. Okay. So this thing you can either draw like this. Okay. You can draw like this. Okay. Now you have R5 in parallel with R6 plus R7. So when you are looking at this circuit, so this entire thing becomes this. Again, you redraw it. This was R1, R3. This is R2. Again, you label it. This point is A. This is would be B. This point would be C. Then D. Then D. Then D. Can you see anything? Yeah, we can safely say that this is a common point. So this R4 and this entire network is in series. Okay, so we can safely say that the entire network. Let me rub this circuit so that we have some space. I want to show you in the same platform so that we can easily see it, how it has to be done. So clearly now this circuit has been reduced to this value. So we can clearly see that R4 is in series with R5. Okay, now let me take the pen again. Okay, now we say that R4 is is in series, and hang a bit. I don't know. Yeah, a little bit slighter. Yeah, sorry for that. R4 is in series with R5 parallel with R6 plus R7. So now we have another network, that is your R1. Okay, then here is my voltage source here. Okay, this is my A point, this is my B point, Okay, let me label it later, because another point R1, this is my R3, this is my R2. So this is my R3, this is my R2. Now I have this point as R4, okay, and this R4 point is in, basically this R4 point I can write like this also. So this point would become R1 plus R5 parallel with R6 plus R7. This is my R4 point. Now again you label it, this is A point, this is your B point. Okay, across this is C, this will also be C, this will also be C, this will also be C. Can you see that? You can see BC is this and BC is this. So we can safely say that R2 is in parallel with this combination, this entire combination. Let me keep the name of this combination as, suppose, X. Okay, so I can safely say that X is equal to R1 plus, for simplification purpose, nothing yet, R5 parallel to R6 plus R7. So I can say R2 is parallel with X. Okay, so my entire thing, this network gets reduced. Now my new circuit would be, this is my voltage source, this is my A point, this is my C point, this is my resistor R1, this is my resistor R1, this is my resistor R3. Okay, and the entire network, this whole network is getting reduced to R2 parallel X, right? Now again, let me write this. This is A point, okay. Across this it is B, then this is obviously C, this is C. So again, if I look at this network, okay, so this point is connected, R1 is connected between what point? So again, if you see, there is a common point here. B is a common point here. So this is a B is a common point. So I can safely say that R1 is in series. R1 is in series with R2 parallel to X. So I can again reduce the circuit. This is my voltage source. Okay, my R1 is in series. So I can, instead of R1, I can write this point. And now I have my R3 point here. This entire network gets reduced like this. Okay. So I have this point here as this point here as this R2. Again, I can label it as A. This is my B point. This is my B point, and this is my B point. Clearly, I can say this entire thing. Let this entire thing be equal to Y. Okay. Let me keep it for the sake of understanding. This be Y. So I can safely say that my Y is between A and B, and R2 is between A and B. So my entire circuit B is can be reduced into one circuit, wherein this is my A, this is my B, and this is my R equivalent. And my R equivalent now would be equal to what? It would be equal to R2 in parallel with Y. So you can substitute these values and get the answer, and you have the R equivalent. This is how we do series and parallel networks. You have to label it, and if you have a single common point between two nodes or between two resistors, then it is in series. If you have a connection that is joining the top and the bottom node, then you have a parallel connection. As simple as that. There will come a circumstance wherein these series and parallel combination is not possible. That is called a star delta transformation. There in the next lecture I'll be explaining you that also. So hope you have enjoyed the lecture and you have understood it. So let me stop it, and if you're new to the channel, kindly subscribe this. And that's it for today, and let's meet you in the new lecture.